Now, just a word of introduction before giving the floor to Purba. Today, there is a second webinar on the AI and water science for this second meeting of the Water Week webinar. So, for H2O Lyon is a research university school, very much like a graduate school, dealing with water sciences, and it comprises all research lab, masters, and PhD training in Lyon and masters. We work on interdisciplinarity, the link between training and research, international relations, and also with the various players in the regions. So we do have a master called Integrated Watershed Sciences, and within this master, students have to organize webinars. Today, this is the second webinar of the week that they are organizing on AI and water sciences. And with no further ado, I will give the floor to Purva, who will be the facilitator.
So, good afternoon, everybody. First of all, a warm welcome to everyone present here on behalf of all H2O team. So, our last webinar went so well, and again, we are here and excited for listening to so many good European professors. So, this is the webinar, as we all know, and we are just exploring the AI and watershed sciences by various European professors. We are having our speakers today. Dr. Zoran Kapelan, who is the chair and professor of urban water infrastructure at TU Delft at Netherlands, and who is going to talk about AI-based methods and solutions for smart water systems. Dr. Heidi Kreibich, who is the head of section hydrology at GFZ Germany, and who is going to talk about machine learning for understanding and modeling flood damage processes. And Dr. Andrea Cominola, who is the head of digital water system groups at TU Berlin, and who is going to talk about insights on AI-powered behavioral modeling for climate and water resilience. And this webinar is being organized by us, IWS H2O Lyon students, me, Purva, Mathis, Kevin, Ricardo, and Sampada. So, if it is good, we can start with Dr. Zoran Kapelan, and you can share your screen, Dr. Zoran.
Okay, thank you very much for this invitation to do this talk today. My talk is going to be on artificial intelligence-based methods and solutions for smart water systems. A little bit about myself. I'm heading the Urban Water Engineering Group at TU Delft. It's a group of 11 teaching staff members with about 30 to 40 PhD students at any point in time. My expertise is in the wide range of topics related to urban water infrastructure, and I will show some of this during this talk. I have supervised quite a few PhD students and postdocs over the years, so what you will see today is mainly their work with my supervision. My research has led to societal impact via the uptake of new technologies. And I'll give you one example today. Yes, I published a few papers, a few citations, got few awards. More importantly, my research has got few awards, which I'm really proud of. So yes, that's pretty much it. So my talk focuses on the urban water infrastructure, and by that I mean the whole urban water cycle. So anything from abstraction of water to treatment, to distribution of water, supply and distribution, to consumption, and then to collection of wastewater and stormwater in urban drainage systems, and then transporting back to the wastewater treatment plants before releasing back to the nature. This infrastructure is changing multiple challenges. You are probably all familiar with this, so I'm not going to spend much time on this. So in addition to the usual suspects, climate change, population growth, and urbanization, which are affecting the water cycle in multiple ways, complex ways. We do have sustainability concerns, obviously, environmental issues caused by pollution and otherwise. At the same time, the infrastructure is not getting any younger. Most of the pipes that are in the ground have been there for a while. And in some countries, in some systems, the replacement rates are insufficient, unfortunately, at the moment. At the same time, despite all these challenges, we are faced with increasing user expectations who would still like to, open the tap and get nice clean water flowing out of it, or when they flush the toilet, they would like that water to go away. So one way to address these challenges is by means of smarter urban water, developing smarter urban water systems. I say deliberately smarter, even though the more common term is smart urban water systems, because that term kind of implies that what we did before was not so smart, which of course is not the case. So what is the main kind of driving force behind these systems? It's multiple things. First of all, with these smart water systems and especially with digital technologies, we want to better understand the network performance state. We want to better utilize all these resources that are required, water, energy, treatment, chemicals, and the rest under normal operating conditions. Then when something happens in the system and something fails, we would like to be able to predict ideally before it fails, or if we can't do that, at least detect as quickly as possible and then intervene. And of course, all this is feeding into the overall asset management and ultimately a service that is delivered to the customers. What you see here in the figure is the layered version of a water system. This is from the Smart Water Networks forum. So I quite like it because layer one is the physical layer. Let me just change my pointer. So the first layer is the physical layer. So this is your system as it existed a long time ago: pipes, pumps, tanks, treatment plants, and so on. At some point in the past, we added sensing and a little bit of control. This happened with the introduction of early SCADA systems back in the 80s. And then this was followed later on by the collection and communication of information with the mobile phone technology and so on, and other related technologies, Internet of Things and so on. And ultimately, all this data that was collected in some historian computer or in a control room of a water company would normally be displayed on a screen to the operators. And this is where we are pretty much at now. But what is really more interesting is this final bit. Sorry. It's the final part, which is the layer number 5. Sorry, I thought something was going to happen. Layer number 5, where this data is fused, which means it is basically the collected data is not just displayed, it's processed to extract useful information, and then this useful information is presented to the operator to make better decisions. There it is. Yeah. Okay, let me give you a few examples of these solutions. The first one I'm going to talk about is the system for real-time detection of pipe bursts and leaks in drinking water systems. So the challenge here is to try and detect and locate pipes or pipe bursts and other failure events like failing valves and so on, and raise alarms in near real time. The data that is being used for this is data coming from the pressure and flow sensors, typically every 15 minutes. There is not much of this data. This work was done in the UK, where a typical density at the time was there was a flow meter with the data log already inlet pointing to this sectorized part of the network, DMA, or district meter area. And there was maybe another pressure device which was measuring pressure at the critical point, maybe another pressure at the inlet point. So only 2 to 3 sensors for a network that could easily have 200 pipes. And this, of course, limits the expectations from any system that is processing this data. The technology I'm going to talk about is AI-based, and it's data analytics type technology, which means there are no physically based simulation models that are used in this, none whatsoever. The only data coming in is the data from the sensors, which is then processed in an automated way together with some additional data, and then leading to the alarms. How does it work? In several principal steps. The first one is you need to predict the sensor signal, either pressure or flow, for each sensor in the system for the near future, say next 15, 30 minutes, maybe an hour, assuming business as usual, assuming no failure events. And this is done by the artificial neural network. And you can see here in those two graphs, 2 such signals, pressure and flow. The blue line is the observed data, green line is the training predictions of the neural network, and the red line is the test on that network on unseen data. And as you can see, there is a good match between predictions and observations. Once you make this prediction, you can start collecting evidence about potential failure. And this can be done in a number of several ways. I'm going to mention only one such way here. So basically, in this case, you make a prediction and then observation comes in. You make a new prediction, observation comes in. Every 15 minutes, you first predict, then you wait for the observation. And as long as the two are close to each other, you can assume that nothing unusual is going on in the system. At some point, the two will start deviating from each other, and this deviation is the first form of evidence that something is going on, maybe a pipe burst in the system. Other forms of evidence are possible to collect, but I'm not going to talk about this to save time. And I just like to know that collecting this evidence is very much where you can build your engineering knowledge into this detection system. And the final phase is then to process this evidence and raise alarms. So in this case, this is done by a Bayesian network, which could be built for each sensor individually or for a group of sensors belonging to the DMA. At the entry point at the top, you feed the network with evidence, and at the output, it predicts the probability, a number between 0 and 1, that there is a failure in the system. And if you then put a threshold value on that probability, you can raise an alarm. The system is, of course, trained initially on some past historical data, but it can also be retrained periodically, as all these artificial neural networks and Bayesian networks can easily be retrained every now and then, maybe every 3 months, every 6 months, once a year, once you have collected new data or new confirmed events. A couple of examples. The first example is large burst. So in this large burst, pressure, when the burst occurs, pressure drops significantly and the flow increases. And this is a large burst, and you could say, okay, but this water is going to appear on the surface quickly. Someone is going to notice this and call the company. True, but if this happens 45 minutes after the midnight, like in this case, it may not happen immediately, and water utility would like to know about it immediately, and perhaps that they could go out and fix the problem before the morning. But anyway, utility would always like to know about these events, to be the first one to know about these events rather than hearing from us. Another example, a bit more complex, is the example of a pressure-reducing valve failure. So this is part of the system which is controlled by a fixed setting pressure-reducing valve, and the pressure shown is the pressure downstream of that valve. And in normal condition, it's near constant. Okay, despite the changing flows, which are following the diurnal pattern with a morning peak and evening peak, at a flow meter, which is at the entry point of this part of the network. At some point, the pressure starts increasing and fluctuating if there is nothing visible on the demands, and this leads to a first pipe burst, which is seen here with a pressure drop and a flow increase. The company went out, fixed these bursts, but the pressure oscillations continued in the coming days, and ultimately this led to a second burst. After that, after fixing the second burst, they investigated and realized that the pressure-reducing valve was faulty, and once that valve was replaced, it was basically business as usual. Now, in those days, this detection system was not used, but if it was used, it would have risen alarm here where the vertical red line is at 12:15, which is almost 1 day before the first burst. What this means is that if they had this system and they had this alarm, they could have went out and detected the faulty PRV, fixed the problem, and they could have avoided those two following bursts altogether. This solution, elements of this solution was, this methodology was first of all successfully validated with historical data, simulated events where we opened hydrants in the field to simulate bursts and real life events. This started as a PhD project in the UK. It was then followed by some knowledge transfer partnership between a large water utility and the university. And eventually it was developed into a commercial solution with some of the elements of the system I've shown you here built into that solution. It enables fast and reliable detection. Fast means usually within 15 to 30 minutes, 1 to 2 time steps that are used to transmit the data, and reliable meaning with a low false alarm rate. The system was used company-wide from 2015. It was at the time processing data initially from 7,000 plus sensors. Then it was increased to 10,000 sensors. And it led to major operational cost savings in monetary units, several million euros per year. Yes, we got few awards for this and so on. But the main thing was, I think all the researchers like to see what they do eventually implemented in practice, especially engineering. The two figures shown here, the top one shows the list of alarms as the operator in the control room is seeing them. In this case, there were several people who were sitting in the control room, and methodology was implemented as a software which was running on a computer, receiving the data from the field. We came up even with some method to rank these alarms, but we let the operator ultimately choose which alarms should be attended to first, and then the operators were, based on the information they were getting, they were sending the teams out to fix problems. Once you double click on any of these alarms, you could investigate further into details. You could look into actual pressure and flow CDAs. Another example of a more recent system, which is also AI-based for burst and leak detection. This one is more sophisticated, more fancy. In this case, we're using now acoustic sensors rather than pressure and flow sensors. The industry is moving in a direction. We're using deep learning, convolutional neural network, supervised and semi-supervised training, data augmentation, transfer learning, all these sophisticated techniques. Now, despite all this sophistication, it turns out that this method is not actually working that much better than the one I just described. And I would like to think there are two reasons for this, and I'm seeing this as a general trend. You can use any advanced AI method, as advanced as you want, but ultimately that the success of that method, the performance will be limited by the data that is fed into that method. And the data in the water industry, which is getting better at collecting data, and it's improving all the time, is still rather limited and sometimes of questionable quality. The other reason is that in this particular example of this system based on deep learning, we just applied the so-called brute force approach. We just took the acoustic signals, labeled them manually, and presented them to the method and expected the method to work. This is different from the detection system I described earlier, because in the one I described earlier, we managed to find a way to build engineering knowledge together with AI into the system. And this was in the form of those evidence collection that I mentioned earlier. Another example of AI-based methods is the water demand forecasting. Andrea will tell you probably more about this, or a different aspect of this in his own talk later on. I'm just showing here, this is an example from demand forecasting models. You can forecast demands long-term for a few years ahead, 30 years ahead, but also for operational reasons, maybe a day ahead or a week ahead. In this case, we predicted demands 7 days ahead at a 1-day time step. And this was smart demand meter data. This was from the Wessex area in the UK. We had data from about 2,000 properties on the consumption from smart meters, recorded every 15 to 13 minutes. And we then went on and developed different forecasting models, up to 8 of those as shown here, with different inputs. And this was done by using different machine learning methods. Gradient boosting turned out to work best, but that's less important. What is more important is we built models, 8 models with different inputs. We tested the models are shown here in terms of accuracy by mean average percentage error. So the lower, the better value. We built the models for all of data for all 2,000 properties as one big group. We developed individual models for 6 smaller geographical areas, those 2 graphs. And we built models for smaller districts, and there are 6 districts in this case. So this is about 2,000 houses. This is few hundred houses, and this is few tens of houses. Top row is using all the data to try and forecast average demand. Lower row of tables is focusing on the peak summer days, with the aim to predict both average flows and peak flows in the system. And what is more important in this case, the models we developed, as you can see, they are working reasonably well, is what you can get out of this. For example, first, if you compare for all the data sets, as you increase the spatial resolution, as you make the spatial area smaller, the best performing model initially has an error of about 2.5%. This increases to over 4%, and then eventually to something like 7%. And this is expected as you group demands into houses into smaller groups. The forecasting error will increase, but this way we were able to quantify this so much. Another interesting thing, for example, you can see from this is that if you look at models 1 and 5, model 5 takes path consumption data, temporal data, which is day of the week, month of the year, and that sort of thing, household data, occupancy rate, council tax bands, anything to do with an indication of the affluency of the household members, and then weather data as well, air temperature, humidity, sunshine hours, and so on. It's interesting to see here that model 1, of course, works the best because it's the most complete one. And you can see that by this model being the lowest position on all 6 graphs. But for example, model number 5, which doesn't have past consumption, works quite well if you compare it in all these graphs. So it's a dashed blue line if you compare it with the best performing one. What this is telling you as an engineer is that if there are houses in the system where you don't have smart demand meter data, you can still forecast demands well by developing the model on the households which have this kind of data, and so on. Another example of AI-based methods is for the detection of failure events and drinking water treatment plants. The good thing about treatment plants is that unlike pipe networks, you have more sensors in a smaller confined area. So in this case, sensors are shown as these yellow boxes. These are different water quality and quantity sensors. So what we did in this case, we first started playing with the so-called the existing event recognition system. This was the company system. This one was detecting these major and minor failures. Minor was the one which is leading to a problem with a single 1 or 2 treatment processes. Major is the one which leading to a shutdown of the whole treatment plant. The existing system was able to detect only 22% of total events with quite high false alarm rate, almost an alarm per day. And this one is based on the flatline thresholds and persistence time. So something like if turbidity sensor shows that turbidity is above, say, 2 MTU, and this persists for half an hour, raise an alarm or something like that. We then tried to modify in simplistic ways the existing system, but that didn't improve much the detection rate or the false alarm rate. Then we eventually went on and developed something which is more AI-based, which significantly increased the detection accuracy, but also significantly reduced the false alarms. And if you compare this, which we did at the time with the Canary software, which is the US Environmental Protection Agency standard for similar thing, you can see we have a similar detection rate, but half the false alarm rate. False alarms are very important for the operators. They simply wouldn't use a detection system, no matter how successful it is in detecting actual events, if it floods them with a lot of false alarms that they need to follow up. Another example of AI-based systems for improving the smartness of water systems is on the bulk water supply system. This is the water quality example, an early warning example. So in this particular case, the system was comprised, it was a trunk main system, which was basically distributing water into individual towns and villages, these DMAs. And there was a whole bunch of flow meters and then a turbidity meter here. And this system had problems with discoloration, with events when water becomes reddish or brownish. This happens in old corroded metal pipes. So what we did here, we developed an AI-based model. I think in this case, it was the random forest model, which was working the best, not the neural network shown here, which was predicting turbidity here by using the data from different flow meters. And this, you can see how this one of those predictions compares to the observations. By doing this, we were able to predict turbidity up to 6 hours ahead of the discoloration event. So we gave utility up to 6 hours lead time to do something about it. Moving on to the urban drainage side of things, you can use AI, for example, to predict rainfall intensity. This is traditionally done by rain gauges or by radar technology, but neither is working ideally. So in this case, I did some work with some Chinese researchers, and we said, okay, why don't we try and predict rainfall intensity from images coming from CCTV cameras? We have a lot of these cameras in the town. Why don't we collect a number of these images, label them based on the nearby rain station, and then train some form of deep learning, in this case, convolutional neural network, to try and predict. And it worked out reasonably well. It could certainly be further trained and improved, but we just kind of proved the concept that this can do the work. And it's not an easy task by any means, because rain manifests itself very differently on different images. It depends what is in the background. Is it day or night? Is it cloudy? Is it windy? And so on. Another example of the use of AI is the more recent example on building the meta model of an urban drainage system, a surrogate model, which is computationally much faster. but equally accurate as the physically based model. And this was done by graph neural networks. And on the left-hand side, you see an error of an urban drainage system in the Netherlands. And on the right-hand side one, you see the predictions of both the SWIM model, which is the physics-based model, and the GN and the AI one. And you can see both predictions are similar, and the errors across the network are small. What is the main advancement here? I mean, these models have been developed in the past. Models that were developed in the past typically tended to predict only at a very small number of occasions and not for this far into the future. So they were never really a proper true surrogate model for the physical model. In this case, we are aiming to predict, in this case, water levels or flow rate everywhere in the system simultaneously and for the whole duration of the rainfall event. Another example from urban drainage systems is detection of blockages. So you see here a combined sewer overflow chamber with a spill level. The upstream catchment is relatively small, so the water level is fairly low when it doesn't rain. Occasionally when it rains, it spills, and that's all fine. However, at some point, even though there was not much rainfall, the water level kept rising, and eventually it was spilling all the time, which was effectively the spilled wastewater. What happened is that the blockage occurred. This occurred because there was a lot of siltation coming from the upstream catchment, which ended up in this. When the company went out and cleaned the CSO chamber, they got a response they were not expecting. Now, at that time, they didn't have the blockage detection system, but if they had it, it would have detected blockage where the vertical red line is, which is only a couple of hours into the blockage start, which is really quick. I mean, this is literally nothing compared to the typical few days or few weeks that this CSO would be normally left undetected. Another example of using AI, this is a more recent ongoing work with KWR in the Netherlands and Waternet, Amsterdam Water Company. We're trying to predict nitrogen emissions at wastewater treatment plants with the aim to ultimately control these, reduce this. But the first task is to predict this. And we started with developing a deep learning method, and it worked reasonably well. And we were motivated by the fact that the physically based model, the process-based model that we used, which was the industry standard, wasn't working that well. And it wasn't working that well because in the bioreactor of the plant, there is bacteria which likes to behave, it almost has a mind of its own. It's basically the process which is not understood well. A number of PhDs are going on at the moment, PhD projects to try and understand this better. So what we said, okay, maybe the physically based model doesn't work that well. The deep learning AI one worked better, but why don't try and combine the two in the physics informed neural network? And that's what we have been doing lately. And that is turning out to work even better. So this is an example of an AI system where you can use AI to make more accurate predictions simply because you don't have a accurate enough physically based model at the moment, or in some cases there is no model at all, like in the case of discoloration I mentioned earlier. AI can of course be used for asset condition assessment as well. So this is basically taking CCTV inspections data, those images like the one shown here, and analyzing those to identify different faults like displaced joints, cracks, and so on. It's a long list of these. This is now done manually by technicians who watch these videos for hours, and it's time-consuming, costly, and this work is inconsistent. If you ask two technicians to watch the same video, their report is always going to slightly different. So we went on and developed an AI solution which is based on computer vision and deep learning. This started as a PhD about 10 years ago. And we were able to automatically detect first faults in images and then to classify them. And this is a really challenging task. The method that was developed so far works well. It's currently being developed further by using several millions of these images that were provided by the commercial partner. So my PhD student who remained in the UK, I left and moved to the Netherlands. He is involved in this ongoing commercialization, and I'm too involved as a sort of advisor. So, final thing I would like to mention as example of AI is the AI for flooding. I'm not going to give you any specific example here. This is an ongoing project, Artifact, between Technical University in Hamburg, IHE in Delft, and TU Delft. And we are developing exciting new models to predict flooding and effects of flooding. The model we are working on at the moment is the 1D, 2D model. So the model which can predict how the water spreads in a given geographical area that comes from an urban drainage system. So watch this space. There is more to come here. Some take-home messages. Hopefully I'm going to finally time this. The first message is AI-based solutions work, and they can lead to substantial savings and improved service. Hopefully, I persuaded you with this brief talk today. I keep reiterating this message because I still see some skeptics in the water industry. Having said this, with the recent developments in AI, with the ChatGPT and generative AI and the rest, and the increasing exposure of, if I may say, ordinary people to AI, it becoming increasingly more acceptable. AI technologies should be combined with engineering knowledge to develop effective leak detection methods, and not just leak detection methods, other methods as well. I've shown you two examples today at the very beginning of my talk, and I'm not seeing a lot of this in current AI tools. A lot of existing AI tools that are in published papers, they typically are based on some off-the-shelf standard AI methods, which are just fed with the data collected somewhere and then tested and then shown that they work reasonably well. So I encourage you all, if you intend to work in this area, to try and be more smart about this. We as engineers, as water engineers, should be able to build our knowledge into these systems, in addition to computer science knowledge that goes into AI. And together we can make better methods and better tools. New, more capable methods should definitely be developed using the latest AI technology and new data. And one final point is about the data sharing. We all know that the water industry, despite best efforts, has limited data, and we as researchers have even less access to even less data. So I've been advocating for this data sharing for quite a long time now, and we are doing some steps at TU Delft to improve this. So please, if you have any data to share, and there are some good examples on the internet already in the water area and infrastructure area, please do your best to share data, but not just data, the models that you developed and so on. This way we can all develop better solutions. Thank you.
Thank you, Dr. Zoran, for sharing your insights about how AI is making our water system smarter. And it was really interesting to know about it. So, if we have any questions from the audience, you can ask and type in the chat, or you can directly ask to Dr. Zoran. Does anybody has any questions? Or, yes,
There
we
is
have a
one.
question.
Yeah, I can see it. What are the challenges of implementing AI for pipe burst detection in a large urban water network? It's a great question, Ricardo. Yes, there are multiple challenges. I would say there are challenges on the technical side of things, but there are even more challenges in persuading people in utilities and companies to do something like this. And my experience with this is the best way forward is to co-develop something with a utility. On this particular occasion, years ago, I was lucky to find someone who was interested in a UK water utility, and they were willing to share some small data set initially with a PhD student, Dr. Michele Romano, and myself. And we went on and developed something, showed them, they liked it, and then they shared more data and so on. So one thing led to another, and eventually we developed quite a nice detection system. Even then, it wasn't adopted by the company management because they were considering commercial solutions at the time and other things. But ultimately, it worked out. I'm not going to go into too much detail. So yes, there are challenges on technical side of things, but that's kind of more under our control. But there are challenges beyond our control or little control, and that's what you have to deal with if you want to see one of those methods, one of your methods implemented.
Thank you, Dr. Zoran, for joining
Yeah.
us and sharing your knowledge with us.
Thank you.
So, we would like to go for our next webinar with Dr. Heidi Kreibich from GFZ Germany, who is going to give us the insights about machine learning for the understanding and modeling flood damage processes. So, you can start, Dr. Heidi Kreibich.
Okay, thank you very much for the kind introduction. So I'm very happy. Thanks very much for this invitation to this online webinar. So as already said, I want to share some insights on machine learning for understanding and modeling of flood damage processes. So now change of topic. So I focus on riverine flood events. And in this respect, I focus on the damages which result from these riverine floods. So this is the approach which is commonly used to describe damage processes due to flood events. So very simple approach. So normally people only look at the water depth in the inundation area and use that as to determine the damage or the relative damage ratio for specific affected sectors, here in this example, residential buildings. But if we look at the, now the slides are not moving. Why is this now? Okay. But then if you look at the empirical data which are behind this very simple figure, we see that there is large scatter. So water depth is often the most important factor influencing the damage resulting from riverine floods, but there are many other factors as well. For instance, the quality of the building, if the flood water was contaminated, if flood-proof measures have been implemented or precautionary measures been implemented, which is reducing the flood damage. So these are also important factors which are influencing the amount of damage. But there are many more. And so what can we do to learn more about this damage process? Of course, one aspect is to improve the documentation of past flood events and to collect more empirical data on the resulting damage due to riverine floods. So this is one example during the flood event in July 2021, which was a very extreme flood in Germany, which mainly affected the areas here in the western part. But what we can see here on the right-hand side, this is showing the stream gauges and their maximum recorded flood levels. We see that also other areas have been affected. So most of the lessons learned studies and documentation and event analysis focused on this area here in the western part in the federal states of Rhineland-Palatinate or North Rhine-Westphalia. But what we can see here, we did a study using natural language processing on basis of more than 26,000 newspaper articles, which all mentioned this July 2021 flood. And what we can see here is that this approach also helped us to gain insights into other areas which had been also affected by this flood event, but which were not so much in focus, like the area in the west here. Another advantage of this text mining approach is that very often during these lessons learned studies and damage assessments, the focus is on this physical damage, so looking at the damage to private assets or to buildings. But in analyzing these newspaper articles, we were able to also put a large focus on resulting damage to individuals, so particularly mental health, but also physical health problems, even loss of life. And on the other hand, also we identified many different aspects in terms of damage to critical infrastructure, which is also particularly important for the reconstruction phase after the event. Also, this text mining helped us to better describe and know what the societal discourse is. So what are the newspapers writing about? This is often very closely related to what people are interested in, what are the political and societal discussions about this event. And we were able to follow these topics during the event, but also a long time after the event. So we analyzed the newspapers of the whole year of 2021 and could see what topics were in the focus of the discussion during the event, but also afterwards. Another aspect or another approach how one can gain data on the consequences of riverine floods are surveys. So actually here at the GFC, we are undertaking surveys after all large damaging flood events which occur in Germany since 2002. So we already compiled a rather large database on damage due to riverine floods, focused on residential buildings and also companies. So our survey contains about 180 questions and tries to describe the whole important processes related to the damage. So of course we ask about the flood damage, but also about the impact parameters like water depth, flow velocity, contamination, duration of the inundation and so forth, but also a lot about the building characteristics, precautionary measures which had been undertaken, early warning, and many more. So quite a broad portfolio of variables which are collected, which all help to describe the damage process. All this data is also integrated in the flood damage database, WHOVAS 21, which is quite a unique database in terms of detail. So how many variables we have for the individual object and number of data sets. So this is a object-specific damage data, which fosters a better understanding and estimation of flood damage. So I want to stress that because in contrast to many other natural hazards databases, which are on event level, this database is focusing on individual objects. So this means individual companies or individual residential buildings, and try to describe with many details the damage process to this individual object. And this can then be used as a basis for analysis, for instance, using machine learning to understand the flood damage processes better. So this is exploratory analysis where we put in this empirical data. And as you can see, just as a visual idea, there are many, many different variables which are strongly related to each other. And we have the loss here in the middle. So we can see that this refers now what I've said at the very beginning, that the loss is influenced by many, many factors, which then in the end also interact with each other. So using different approaches like elastic net, random forest, XGBoost, for instance, we can then analyze this data set in a way to identify the feature importance. So how important are the different components in terms of driving the damage? And what we can see is that water depth is, as expected, one of the most important variable to determine the amount of damage, but also other parameters are important. So in one study, we developed an automatic workflow for this feature selection and then following loss model development. So we used quite a large set of different potential predictors for the flood loss, and then used an automatic feature selection to identify what are the most important parameters in this specific case. So multilinear regression was used, and then using the F statistics and selecting the K predictors, we automatically came up with the selected features, which are under these flood circumstances, the most important parameters. Then these were again used as input for the systematic structure learning of a Bayesian network. Bayesian network is a probabilistic tool or probabilistic approach which we can use for developing a probabilistic flood damage model. And we use that to identify the optimal network. So this here are the results of this feature selection workflow. So in the first, we see how many different features were used to predict the target value, which is the relative damage in this way. And so we, following this graph here, we identified 7 features to develop the flood damage model. So next to the water depth, this was also the flood experience, the elevation of the building, and so forth. Then we used different structure learning algorithms. So for instance, the hill climbing, incremental association, max-min hill climbing, general two-phase restricted maximization. So we tried different approaches to develop the structure of this Bayesian network. So as said, the target variable is the relative loss. And then using these different approaches, we came up with similar but a little bit different networks. So water depth is always closely related to the loss, but there are also other parameters which are important. So what is now the particular feature or the big advantage of these probabilistic damage models? This is that in the end, we do not only come up with one number, our estimate for the resulting damage, but we come out with the whole probability distribution of the expected damage. So as we see here, as most of the data is related to rather small damage numbers. So we have often quite focus on the small losses. So this is particularly difficult, and this here is showing the big challenge. So due to the structure of the underlying data set, it is very, very difficult, or it's a big challenge to, for instance, estimate total loss. So in this case, relative loss of 1 means the building is completely destroyed. So total loss of the building. But as this is shown here, we were not able to really predict that. So this is still an open question how to improve this method to even also be able to estimate these extremes. But on the other hand, the big advantage of this probabilistic multivariable loss models is that they improve the description of the damage process and as such reduce the uncertainty. But on the other hand, probably even more important is that they inherently provide quantitative uncertainty information and thus support better decision making, so that the decision makers have the whole bandwidth of possible outcomes and then can decide by themselves in terms of their preference, if they are rather risk-taking or want to be more conservative, to decide on the particular measures how to mitigate the damages. So here I want to show one final example about one of these probabilistic flood damage models, which we in the end also applied on a European scale. So our target variable is the relative building loss of residential buildings. We have the hazard parameters, water depth and return period, which are directly related or drivers of the loss. And they can be easily estimated on basis of hydraulic simulations, for instance. On the other hand, we also have vulnerability parameters like the state of precautionary measures which had been undertaken at the individual residential buildings. As this is not known and basically impossible to predict on a large scale, we used their parent nodes like the flood experience and the building characteristics or building footprint to estimate the probable state of precaution, and as such also use this vulnerability influences to estimate the relative building. So we used input variables which were available open access. So for instance, the building footprint area and the building characteristics were derived from OpenStreetMap data and the historic flood events. So estimating the flood experience of the people in the different regions. This was based on the Dartmouth Flood Observatory, which contain all these different inundation areas or flood events which had occurred during the last 10 years. Then applying this probabilistic model, as that we do not only come up with one map of resulting damage, as shown here, we have the 50% quantile, but we can also show the 20% quantile and the 80% quantile, so a small possibility of resulting damage and a quite extreme one. And so this can then be provided to the decision maker so that they can see the whole bandwidth of possible outcomes of such an event. And with this, I come to my conclusions. So the collection of empirical vulnerability and damage data is essential to better understand flood damage processes. Machine learning-based feature importance and Bayesian approaches support the process understanding, and the probabilistic multivariable damage models improve the description of the damage processes, reduce and inherently quantify uncertainty of the damage model. And with this, I thank you for your attention, and I'm looking forward to some discussion. Thank you.
Thank you, Dr. Heidi. It was really interesting to know that how crucial a flood damage study could be, and it was really interesting. So I would like the two audience, if they have any questions, they can ask now. Until waiting for the questions from audience, I would like to ask a question to you that as you said that studying flood damage is crucial and it is important. So how do you decide the variables, like as you said that it is mental effects of flood or physical buildings and everything else. So how come you came to know that which variables should be there to study?
Okay, in terms of variables, we did at the very beginning, before we started the first survey, we did a Delphi method. So this is in several ways. You ask different experts which are dealing with flood damage processes. So these were, on the one hand, scientists, on the other hand, also practitioners from the administration who are responsible for flood risk management. And the third cohort were from the insurance industry, because they deal a lot with the damages due to riverine floods as well. And so we ask these experts, more than 100, what they think are the main drivers of flood damage. And as such, we had a basis or a very long list of potential variables to ask for. And this we used as a basis to develop our survey.
Okay, thank you. And we have a question in the chat box from Sampada, and she's asking, you said AI is used to select relevant parameters to assess flood damage for individual components like houses. How do you ensure that the features selected by AI are meaningful, and what might be the accuracy of AI?
Okay, how do we ensure that they are meaningful? I mean, it's a result of the data. So, of course, we do a lot of quality control to collect and compile meaningful data samples. So this is one aspect. And the other aspect is before we use these these identified parameters to develop flood damage models, we also compare it with, let's say, expert judgment on the one hand, and with available and already used in practice damage models. So to have on both hands, do quality checks within the system and use external knowledge and external aspects to compare what we came up with.
Okay, thank you for the answer. And we have another one. Given that the accuracy of AI-based flood prediction relies on data availability, how can this method be applied on data scarce regions? Are there approaches to ensure reliable prediction? Is this kind of context?
Probably in areas where you have very limited data available, you can probably not start with this feature selection. But what the advantage is from this Bayesian networks, for instance, that they can be developed based on a combination of data and expert judgment. So if you want to combine that, this is a very good approach, because you can use the knowledge of local experts who know the flooding situation and the damage situations in the area and combine this with limited data, and still you are able to develop a probabilistic flood damage approach.
Thank you, Dr. Heidi, for giving your insights and giving us the knowledge about the flood damages.
I thank you very much.
So now we will move forward to Dr. Andrea Cominola from TU Berlin, and he is going to talk about insights on AI-powered behavioral modeling for climate and water resilience. So it's on you.
Yes, thanks a lot for the kind introduction. And I guess you should see my screen correctly. Otherwise, just let me know if there's any issue. And thanks for the invitation. I'm very happy to actually present this after Zoran and Heidi's presentation, because I think what I'm trying to convey in this presentation is a little bit of something complementary. So I'm going to look into the human factor. And I'm going to look into how we can basically discover some human behaviors using AI. I'm going to focus on one aspect that's mostly related to floods. So that also comes naturally after Heidi's presentation. But at the end, I'll give a couple of insights that connect also to Zoran's presentation. So to say, what I'm presenting today can be somehow transferred to different tasks. And as the focus is on AI, actually, and we live in a world of AI-generated content, I actually instead decided to use as a background here some human-made drawings. Actually, this come after Leonardo da Vinci, with a man actually sitting and some drawing about water fluxes. That's from the water studies of Leonardo da Vinci. And I think I'm going to try to combine the two things, water and humans. So in that sense, actually, where the content of this presentation delves into this coupled system, water systems and human systems, which is framed into a larger framework, if you wish, of coupled human and natural systems, where natural systems, of course, go a little bit beyond what's just water, but there's more than that. And now what I'm going to present is based on a fairly recent study that we've completed with a former PhD student. But this concept of coupled human-natural systems is actually not new per se. So this is actually a concept that was presented already in 2007. This is the year in which this science cover is actually taken from, and where there was this paper about the complexity of coupled human and natural systems. So just to set the ground for this, I think, coupling humans and natural systems in terms of how we can model them, how we can study them, and how we can manage these systems of systems is fairly fascinating, because both of them, first of all, are quite dynamic in the sense that they have their own internal mechanisms, but these mechanisms also change over time, and we can expect these to change even to a faster pace and more often in a world that is basically what Zoran and Heidi have presented. More connected, more technological on one side, but subject to faster societal and climate change on the other hand. And in fact, in this paper, the authors highlighted quite a lot some opportunities and challenges, let's say, related to studying these coupled systems, which are listed in this list here in the slide. So, nonlinear dynamics, feedback loops, time lags, resilience, heterogeneity. They also mentioned then surprises. I'm not going to go in detail into that, but basically from the other top 5 elements here, the message is this: studying these systems is certainly not easy, because they hinder a lot of challenges that relate to these internal dynamics, the feedback loops, and then time, and I would even add space dimensions, in which these two systems, humans and water, operate, interact, and influence each other. Now, just to also complement basically this sort of background information, well, why are we studying human behavior? Well, I guess there's been an increasing attention towards human behavior in relation to water in the last years. And to some extent, it is surprising that only comes in the last years. If you think of this image, this is actually the water cycle as depicted by the USGS. So this is also sort of an official source. Basically, in 2022, so just a few years back, 4 years ago, that's when this water cycle was revised in such a way that human activities were highlighted. You see it here in these 3 highlights: municipal water use, industrial water use, and agricultural water use. Before that, the former version of the water cycle was mostly looking at the natural component of it. But now, of course, we need to recognize that the human influence on the system is very major, I would say, and so we cannot really just ignore it. So it's quite surprising, actually, that this comes only 4 years ago, basically. There's, let's say, if we consider the literature in the last 10, 15 years, actually, there's really a lot of papers and research that really motivates, pushes and justify integrating human behaviors in studying these human water dynamics. This is just an example related to floods and disaster risk assessments, but there's really a lot of scientists advocating for better representation of human behaviors into our hydrological, hydraulic, and climate models. As I said just a couple of minutes ago, it's not easy to study human behaviors in these coupled systems, and there's not really a unique or straightforward way to do it. Generally speaking, we can think of 2 macro categories of methods that we can use to study human behaviors. You see them here in the slide with a very simple sketch. We have descriptive models and normative models. Generally speaking, descriptive models, as the name says, tend to give a description of human behavior. So normally the realization of a human behavior is observed. So we have some observations. In this case, it can be like this guy that's just walking. We see the position of this guy over time, and then we can create a model of this guy walking the direction, basically. So we start from observations to describe basically the behavior. There's also normative models, which instead are somehow assuming that humans are agents that behave with some sort of rationality. So their actions actually are implemented in such a way that a reward corresponds to an action. So there's a specific goal, or maybe many goals, that an agent wants to optimize, and the behavior is a function, basically is a sequence of actions that aims at optimizing that, let's say, that objective. So you see here there's a target represented here with a red flag. And this guy is not just walking randomly, maybe at the beginning, yes, but is basically having the objective of going to that red flag. So there's some objectives, there's some rationality, and the goal is to basically really define the rules and understand the rules that are guiding these behaviors. Now we stick to the left-hand side of these two categories for this presentation, actually, because what I'm going to present later, in fact, is a study where we developed a description of some human behaviors. Both, let's say, categories of methods come with challenges and, of course, also suitable modeling techniques. You see some here like feature engineering, unsupervised learning, explainable AI, things that have been already mentioned in the previous two presentations. Of course, when we stick to the left-hand side, and this is maybe a highlight I want to mention for this slide, when we stick to the left-hand side where we want to describe behaviors based on observations, we need to have observations. So we discussed already with Zoran, the data when we want to train AI models are quite essential. And this is really the case also here. We need to have observations to then infer behaviors in a descriptive model fashion. Now, let's give an example, and this is basically the core of my presentation on how we can infer, in fact, human behavior starting from data and which types of human behaviors we look at. In the example that I'm giving here, I'm focusing on flood resilience, and we implemented an interpretable machine learning method that actually replies to this question: how do heterogeneous socio-demographic characteristics and human behaviors influence flood resilience? So to say, going back to this general schematic where somehow on this right-hand side here, where, water influences human systems, in this case, basically the hazard or risk basically is caused by floods. And we wanted to understand how humans actually relate to that. I'll get into the details a bit more in a second. And so we are in the realm of flood resilience. And you see also a little map of the United States, because that's basically the case study that we analyzed. And just to give a little bit of context on that, the reason actually why we analyzed that particular case is related to two main factors. One that is really motivating the relevance of the study. If you look at this map, for instance, this represents the annual losses due to floods in the US in millions of US dollars. You see that there's some significant numbers, particularly on the west and the east coasts, where most of the major cities are. So the actual losses are where the highly populated counties are, and mostly on both coasts. So this is a topic that is relevant for the whole country. And if we look at the future, basically here is just some results from some projections under future scenario RCP 4.5 up to 2050, then you see that actually the increase here, the color is proportional to the increase in percentage, and there's going to be increase larger than 20% exactly in the same areas that are already at high risks. So there's some areas which are really vulnerable now. They will become even more strongly hit by floods and other hydroclimatic extremes in the future. Therefore, this is a compelling and relevant case study itself. The second reason is also very practical. There's some really nice data that we could use in this case study and are collected at the country level, basically, for each individual county. And what did we want to look at? So let's get a bit into what behaviors are for us in this context. If you think about the case of flood resilience, basically, there's actions that both individuals and communities can take to improve resilience. And examples at the community level, or let's say top-down approaches, which are more institutional and related to governance and regulations, would relate to the flood alert systems, for instance, infrastructure systems, which are very expensive and require planning, which individuals cannot do alone, of course, and incentives to promote individual measures. On the individual measures, so here's the little house that I'm representing in the slide, people can do several things to actually reduce the impact of a flood. For instance, some house renovation by maybe even raising electrical sockets when you have a basement so you don't cause a blackout in your home, or maybe by raising houses in such a way that you prevent basically flooding of your basement or the ground floors. Among these, there's also one type of measure, which is the subject of our study, which is purchasing a flood insurance. And so our behavior in this particular study, the behavior one study, is about understanding basically when and somehow why people purchase or do not purchase a flood insurance at the household level. Actually, Nadia, who is the PhD student who actually performed this research, also sketched this in a really nice way. I like a lot this sketch that she made, where basically she represents different agents and there's motivations for them of maybe taking up or not purchasing a flood insurance. So, like for instance, this guy said, "My friend in Georgia got flooded, so I bought an insurance." Whereas this other lady here says, "Well, I'm too young to worry about this. I'm not going to buy one." We wanted exactly to understand to which extent people buy or not buy or don't buy flood insurances in the US, and have a study of the drivers for those behaviors. And the way we implemented this is on a data-driven model. As I said earlier, it's an observational study where we start from data. There's massive amount of data that we could use. And these data are coming primarily from the US Census Bureau, which provides the socioeconomic features, more than 400 features. And in this data set, we also include some features related to experience that people had in terms of experiencing previous floods. And there's another data set, which is basically the output of our model, which is a record of flood insurance policies purchased per housing unit. This spans around about 72,000 records. And this is coming from the NFIP, which is the National Flood Insurance Program that regulates flood insurances in the United States. The relationship between the two, basically, so which socio-demographic characteristics have a relation with buying or not buying an insurance, and was actually implemented by us in this case with a gradient boosting framework, so LIGBM, again, some data-driven model, where basically we used this model to predict flood insurance as a function of socioeconomic features. And on top of this, we also added some explainable AI to understand which inputs are driving the output in a certain direction. In other words, which sociodemographics are pushing people to purchase or not purchase a flood insurance. We did that with SHAP values, which are let's say, a set of indices for explainable AI. The research contribution before going into the result is actually a threefold, because as compared to previous studies, what we've done here, thanks to this availability of data, actually, we could do a US-wide analysis, where previous studies were mostly looking into small-scale studies, maybe in the best case at the scale of a state. And here we look at the whole continental US, so we go large scale. This also allows some spatial transfer, whereas most of the previous studies that maybe were also based on individual surveys or so didn't have a proper validation. Here we actually train, validate, and test our models and generate different models both at the US scale and for individual states. And finally, here we have a purely data-driven analysis, where, as I said, previous studies mostly related on survey data, which of course may contain some bias and subjectivity. So I guess in general, these three contributions are substantiating the novelty of this study as compared to the previous ones, with the overall goal of aiming for results generalization. So let's look into the key results, and I'll keep it rather short in this case. I want to communicate mostly the main highlights. And the first one is that the first general behavior we found is that people have a reactive behavior. If you look at this is a heat map where basically on each row corresponds to a potential driver, and each column to a model for individual states, or the last column on the right-hand side, the aggregate US models. And the features that are on top basically are the most important features that relate to the insurance behavior. And what you see, the first two or three actually are flood history, insurance type, and CRS. I get into more details. But the first one is basically flood history, which means those that experienced a flood in the past, either in terms of big floods, magnitude, or frequency, many floods, then tend to purchase a flood insurance. And that's a bit controversial if you think, because normally one wants to purchase insurances before the damage happens, right? In order to be protected from the damage and have a fast recovery, not to purchase it later once it's already too late to get basically the repayment for the damage, right? But this means basically that we have reactive behaviors mostly. And this is actually also seen from these two maps, where on top you see the flood frequency, and you see that flood happens more frequently exactly on these coastal areas, particularly the east coast here. And this corresponds also to a red color in the map below, which is proportional to people being more willing to take up an insurance when they experience flood frequency. And a typical behavior that you would see actually is represented by this time series, where the take-up rate of insurances, measuring the percentage of insurance in a county, tends to basically be stable or slightly go down in a period where nothing happened. When then a flood happens, everyone, well, not everyone, but more people are purchasing an insurance. So this goes up. And then there's a time to forget. So if people then start feeling safe after a long time without floods occurring, then they basically don't renovate the contract. So first thing that we could reveal by this expandable AI framework is that there's a reactive behavior. The second thing relates to top-down policies. There's this, the emphasis here is on the right-hand side maps. Access to insurances in the US is regulated by the community rating system, which is basically telling, regulating how easy people can get access to insurances. And here you see the blue areas is where this community rating system is very active and where people have easier access to insurances. And in fact, you see that this works because also in this way, in this map here on the bottom, these areas mostly have maybe a bit lighter than before, but still red color. That means that this sort of incentive scheme of the community rating system is working. So apparently there is a good push by this incentive for people to actually be incentivized to take up insurances. And on top of this, actually, the good news is that this is not just effective, as shown by these maps, which is basically a highlight of the previous ones, but also is non-discriminatory in the sense that if you look at these different variables, which are basically those that can relate, that mostly relate to the community rating system, the community rating system is not really having a preference for certain parts or segments of the population. So it's in per se non-discriminatory, which we found sort of to be a good news. But the question is, what's equal and what's the difference between equity and equality? Because if you look at some new results where we actually asked ourselves, are we doing enough? Then you see that there's trade-offs between social vulnerability and risk perception. So if you see now in this plot, for instance, the red dot represents social segments that are highly vulnerable from a social perspective, and they have a lower risk perception, but also a high flood damage. So apparently not everyone in the community is having the same vulnerability, the same risk perception, and the same flood damage. So in order to compensate for these differences, probably we're not doing enough, because it's not just enough to have a non-discriminatory system, but also rather to try and have different incentives that they might fill in these gaps of vulnerability and risk perception. Now, this is basically a quick overview of this study, and I'll be happy to reply to questions if you want to know a bit more in detail. I'm moving towards to the conclusions now by just basically expanding a little bit. As I said, this was an example on flood resilience. Behavioral studies can and actually do go beyond flood resilience. And Zoran, for instance, mentioned water demand management and conservation. So in this case, we would be on the left-hand side of this schematic, more on water usage, conservation, and so on. We can use similar technologies, of course, different data, for understanding also how people use water, for instance. And the behavior in this case would be basically water consumption as driven by a lot of possible determinants, which I'm displaying very quickly on this slide. But so to say, people can use water in different ways depending on some variables that we can observe, for instance, if you have a garden or not, but also some that are more subtle, related to psychology, preferences, and so on. So behavioral studies allow to dig into these types of behaviors. And just as two quick examples, one could look into, for instance, when one uses specific end uses during a day. You see here an example for a shower or a clothes washer, and try to understand what's driving these and how to make these behaviors more efficient. Or rather, you can look into a time dimension. We studied, for instance, for California, water consumption at the household level for more than 20 years to understand basically how people would behave during drought and recession periods, and also the pandemic, the health crisis, and how they responded to these different conditions. So these are just some very quick examples to basically convey that these behavioral studies, now that we have an increasing amount and a better amount and quality of data, can be really done for different goals. So let's get to some key takeaways. We've said that AI and new sources of data are enabling behavioral studies. I think I said it multiple times, and this can happen in climate adaptation and water resilience. We have data-driven evaluation of current behaviors and policies. So basically, it's not just about purely description, but we can use our descriptive models actually to also understand whether policies, see, for example, the community rating system, is effective or not. And at the same time, there's always this doubt about too many data, too little data. Zoran already said that situation with data is getting better, but still, compared to other sectors, maybe in order to really go data-driven and have full validations, full transferability, and so on, we're still lacking a bit behind. So there's also open questions that come with these takeaways. The first one is, what behaviors are identifiable and which ones are decision relevant? Of course, we don't want to just describe behaviors because we have some data and technologies, and so let's do it because it's fun. There should be a purpose, right? So the purpose in this case is mostly behaviors that relate to critical decisions in water. This also leads to understanding what are the real water management implications, and so how we can move from a description to actually actions that inform stakeholders and decision makers. And finally, what about transferability and generalization? I already commented on this and on how there's still limitations into validation of some methods and into transferability between contexts where, besides the regulatory context, also the data context is very different. So these are all points for future research and discussion, and I'll close here, and thank you very much for your attention.
Thank you so much, Dr. Andrea, for sharing us your knowledge about flood resilience. And it was pretty interesting to, like, even if I don't belong to this field, but it was really interesting for me as well to know more about like flood insurance and everything, because generally it is known that flood is mostly all about physical appearance, like the damage and everything, but mental damage and insurance and everything, it's really interesting. So thank you for this. And we have a question from Sampada. Thank you for the presentation. I'm very much interested in data-driven evaluation, but also I want to know the effectiveness of data-driven model in economically poor countries who have been facing the flood and climate change challenges.
Yeah, well, I guess a few minutes are not enough actually to discuss this, because this opens really a very crucial point. What I can say is, of course, there's heterogeneous conditions in terms of data that are available for these types of studies. And for instance, that's actually what I said also when I introduced the US case study. I said really practically we could do it there because this data set was available there. And because that data set and the research questions were relevant for that context. So I have to say, of course, other parts of the world, and depending on the problem, is not always the same areas. But of course, the data situation is very heterogeneous. So in that sense, I don't have a full assessment. There's, of course, as I said, limits to transferability. Within one idea that we're developing and hopefully evolves in a PhD program in the future, actually, we would like also to assess the transferability of similar models Not just to say, well, here you can use them because you have the data, here you cannot really use them because you don't have enough data, but try and see what's the limit to that, where we can come up maybe with assumptions to fill some data gaps at some point, where we can maybe use some proxies of other data. So in that sense, I think there's really a lot of room for research, and we are ourselves also trying to develop strategies for that. But that's certainly a question that remains open. And if somebody has a nice case, actually in maybe some countries, as mentioned in this question, that are relevant and for which studies can be developed, we're happy to engage into discussion.
Okay, thank you for your answer. Maybe we can conclude the webinar. I would like to thank all of our speakers for spending your time with us and giving us the knowledge when sharing it with us. Thank you, Dr. Andrea, Dr. Heidi, and Dr. Zoran. He left already, but thank you, every one of you, and thank you, the institution you guys belong from. And I also would like to thank our institute, H2O Lyon, because it was really a nice experience to organize the webinar, because we all are international students and we are studying in France, and they gave us the platform where we can explore ourselves and we can make connection with such knowledgeable professors like you. So I'm very thankful to H2O Lyon, our professor, the Dr. Shaki and Dr. Maya Clelis. Thank you for all the support and help and motivation to us. And I would also like to ask my colleague Mathis to give his insight, and I would like to ask my colleagues to say how the experience of organizing a webinar went for them. So yes, Mathis, you can start.
Yeah, so yeah, like Spurva said, a really big thank you to both of you for participating in this webinar. It was really a nice experience to talk to you and to try to make this webinar a great one. And thanks to all my colleagues for the help for organizing this webinar.
Thank you very much, H2O. And yeah, also, I think it's a great idea to ask students to organize webinar and contact researchers internationally. Always great topics, always good learning, and also good exercise to produce an event. So thank you very much.
Thank you, and you can go, Ricardo.
Hey, good afternoon, everyone. I would like to thank you guys to attend this webinar, which is actually part of our school project. So we organized this within students and with the help of our professor to gain some event planning skills and scientific organizational and communication skills. And thank you so much, professors, to set times aside to attend this, to communicate to us some knowledge about the use of AI in the water domain. And also thanks for the H2O Lyon staff to help us to organize this meeting. Thank you.
Thank you, Ricardo. Sampada, you can share your thoughts as well.
Thank you for giving me the speaker. Okay. And first of all, I want to thank to H2O Lyon for giving this wonderful opportunity for us to organize this webinar, and not limiting our goal just in the advancement in creating the artificial intelligence. We try to create a meaningful discussion on how the technology can be addressed on most pressing environmental challenges. And from this webinar, we launch new ideas, and we get much more inspirations about the technicals, the collaborations, and practical solutions. And it helps in advancing our missions and helps in sharing our responsibility. And I also want to thanks to all the speakers and the participants here who has been listening to us as an audience. And I want to give a special thanks for Claire Liz, who has been always helping us throughout this journey. Thank you.
Okay, so it's our huge gratefulness towards all the speakers, all the audience, and our H2O Lyon staff. So hopefully we will see you soon if we will arrange some other webinars, or hoping to meet you also soon. Thank you so much. It's me, Purva Bhatt, signing off from Lyon.